Hello students, I hope you all are doing good. So today we are going to discuss NCERT Exemplar of chapter Atoms. This is the disclaimer. Let's start by looking at what you will be able to do after this lecture. Our focus is on atoms and we will build up your understanding step by step. First, you will learn about Bohr's atomic model, its main ideas or postulates, and see how it helps us calculate things like the energy levels and orbital radii of electrons in hydrogen-like atoms. Next, you will be able to apply quantum principles to solve real problems. This include understanding atomic transitions when electrons jump between energy levels and calculating the energy absorbed or released. You will learn about binding energy, which is the energy needed to remove an electron from an atom, and see how Coulomb's law sometimes needs to be modified at very small atomic distances. Let's see the index of topics that we are going to discuss today. There are total 29 NCERT exemplar questions in chapter Atoms. And in this lecture, we are going to cover 6 specific questions numbered 12.1 to 12.6. Let's examine a multiple choice question about the radius of lithium plus ion, lithium ion with 2 electrons removed in its ground state, using Bohr's model of atom. Notice how the question gives the Bohr radius A0 as 53 picometers and asks you to compare the radius of lithium to this value. This type of problem tests your understanding of how the Bohr model predicts atomic radii for hydrogen-like ions with only one electron like lithium and how the radius depends on atomic number Z and principal quantum number N. 4 options are given and you have to choose the correct one. So here the correct option is C, that is 18 picometer. Let's see the solution. So let's start by thinking about how to approach this problem. We need to recall the formula for the radius of an electron's orbit in a hydrogen-like atom according to Bohr model. The Bohr model gives us a specific formula for the radius of an electron orbiting a nucleus. For hydrogen-like ions which have only one electron, this formula is especially useful. The formula is Rn equal to n square A0 upon Z. Now let's break down what each variable in the formula means. So first, Rn is the radius of the electron's orbit. This is what we are trying to find. Next, n is the principal quantum number. For the ground state, n equals 1. This means the electron is in the closest possible orbit of the nucleus. A0 is the Bohr's radius, which is given as 53 picometers. Finally, Z is the atomic number of ion. For lithium lithium has an atomic number of 3. So Z equals to 3 for lithium ion. This means the nucleus has 3 protons, and since it's lithium it has lost 2 electrons and only 1 electron remains. First, let's identify the atomic number of lithium. Lithium has an atomic number of 3, which means it has 3 protons in its nucleus. Now let's consider the lithium double plus ion, written as lithium with 2 plus signs. This means the atom has lost 2 electrons, so only 1 electron remains. The effective nuclear charge, or Z, that this electron feels is still 3 because all 3 protons are still in the nucleus. For the ground state, the principal quantum number N is 1. This means the electron is in the closest possible orbit to the nucleus, which is the lowest energy possible. Let's use the formula for the radius of nth orbit in the Bohr model. Rn equal to n squared times A0 divided by Z. Here Rn is the radius of the orbit, n is the principal quantum number, A0 is the Bohr's radius, and Z is the atomic number. Now let's substitute the values into the formula. For n equal to 1, A0 equal to 53 picometers and Z equal to 3. We get R1 equal to 1 squared times 53 divided by 3. So now let's see how we calculate the radius for lithium plus plus in its ground state. The formula for the radius in Bohr's model is Rn equal to n square a naught upon z. For lithium plus plus, n equal to 1, z equal to 3. So R1 equal to 53 upon 3, which gives us about 17.67 picometers. Notice how increasing z, the nuclear charge, pulls the electron closer, making the radius smaller. Rounding our answer to nearest whole number, we get R1 approximately equal to 18 picometers. So to summarize, the radius of the lithium plus plus ion in its ground state is about 18 picometer. Okay, this shows us that as the nuclear charge increases, the electron is held more tightly and the atomic radius decreases. Let's examine a conceptual question about the binding energy of a hydrogen atom and how it changes if we switch our frame of reference. The slide presents the formula for the binding energy of a hydrogen atom, B equal to minus me square upon 8n square epsilon naught square h square, where m is electron's mass, E is the charge of the electron, n is the principal quantum number, epsilon naught is the permittivity of free space, and h is Planck's constant. Notice how the formula shows that binding energy depends on the mass of the orbiting particle, here the electron, and it gets more negative for lower n values. The question asks what happens if we switch to a frame where the electron is at rest and proton moves around it, and whether we can just replace m with capital M, that is proton mass, in the formula. 4 options are given and you have to choose the correct one. The options explore ideas like whether quantum number change, if quantization applies only to electrons, if the reference frame is valid, and if the proton's motion would still be circular. So notice how the question asks what happens if we switch to a frame where the electron is at rest and the proton moves around it. The correct option C, the frame where the electron is at rest, is not inertial. Let's think through the problem. The electron is said to revolve uniformly around the nucleus, which means it experiences centripetal acceleration. Remember, a centripetal acceleration is always directed towards the center of the circle, and it's what keeps the electron in orbit. Notice that if we try to analyze the system from the electron's rest frame, we are actually choosing a non-inertial frame of reference. In physics, an inertial frame is one that is either at rest or moves at constant velocity, no acceleration. Since the electron is accelerating, its rest frame is non-inertial, and the usual formulas for binding energy don't apply directly. So the main reason for binding energy formula with the proton mass is incorrect is because the electron's rest frame is non-inertial. First, let's recall the standard formula for binding energy of a hydrogen atom when the nucleus is considered fixed. The formula is B equal to minus me raised to power 4 upon 8n square epsilon naught square h square. Here B is binding energy, m is mass of electrons, E is elementary charge, n is the principal quantum number, epsilon naught is the permittivity of free space, and h is the Planck's constant. In this formula, m stands for electron mass, and electron is much lighter than the proton, so its mass dominates the calculation. This formula comes from the Bohr's model, which treats the electron as a particle orbiting a stationary nucleus. The nucleus is assumed to be infinitely massive compared to electron, so it doesn't move. Because almost all the mass in the atom is concentrated in the nucleus, the center of the mass is very close to the nucleus itself. That means for practical purposes, we can consider the center of mass to be at rest when analyzing the atom's behavior. So the frame of reference where the nucleus is at rest is considered an inertial frame. An inertial frame is one where Newton's law apply without needing to add extra fictitious force. Let's examine what happens if we choose a frame where the electron is stationary. In this case, the proton would be moving around the electron, which is the opposite of the usual picture. The problem suggests that by using similar reasoning, we might write the binding energy as B equal to capital M e raised to power 4 upon 8n square epsilon naught square h square. So here is the formula: B equal to minus M capital M e raised to power 4 upon 8n square epsilon naught square h square. Notice that if we substitute the proton mass, which is much larger than the electron mass, the binding energy would be much greater in magnitude. But is this really correct? So this expression is actually incorrect because the frame where the electron is at rest is a non-inertial frame. First, let's consider what happens when we try to use a frame of reference fixed to the electron. In the original setup, the electron is moving in a circle around the proton, so it's accelerating. If we now fix our frame to the electron, our frame itself is accelerating along with the electron. This is important because the law of physics, especially Newton's law, work best in inertial frames, that are not accelerating. The Bohr model, which gives us the binding energy formula, assumes we are working in an inertial frame, usually the center of mass frame where the system as a whole isn't moving. In this frame, both the electron and the proton move around their common center of mass, but the calculations are based on this balanced non-accelerating perspective. If we switch to a non-inertial frame, like one fixed to the electron, the basic assumptions of Bohr model no longer hold. If we try to analyze the system from the electron's frame, which is non-inertial, we have to introduce so-called pseudo forces or fictitious forces to explain the proton's motion. These extra forces complicate the situation and make simple Bohr model formula invalid. So just swapping the electron mass for the proton mass in the formula doesn't work because the underlying physics changes in a non-inertial frame. First, notice that in reality both electron and proton move. They both orbit around their common center of mass, not just one around another. This is a classical example of a two-body problem in physics. It's important to recognize that the motion of both particles affect the system's energy, not just the lighter electron. To handle this correctly, we introduce the concept of reduced mass written as mu. The reduced mass mu is calculated as mu equal to small m capital M upon small m plus capital M, where small m is the electron mass and capital M is the proton mass. So to answer this, let's introduce the concept of reduced mass. The formula for reduced mass is mu equal to m capital M upon m plus capital M, where m is the mass of electron, capital M is the mass of proton. Okay, here m stands for electron mass, which is 9.1 into 10 to the power minus 31 kg, and capital M is proton mass, which is 1.67 into 10 to the power minus 27 kg. Since the electron's mass is much smaller than the proton, the reduced mass mu is approximately equal to small m, the electron mass. This means that in practice, using just the electron mass in the binding energy formula is a good approximation. First, let's recall that the correct way to handle two objects orbiting each other like the electron and proton is to use the concept of reduced mass. The reduced mass, written as mu, takes into account that both particles are moving. Here is the binding energy formula using the reduced mass: B equal to minus mu e raised to power 4 upon 8n square epsilon naught square h square. In this formula, mu is the reduced mass, E is the elementary charge, epsilon naught is the permittivity of free space, h is Planck's constant, and n is the principal quantum number. The original formula B equal to minus small m e raised to power 4 upon 8n square epsilon naught square h square uses the electron mass m instead of reduced mass. mu. This is a good approximation because the proton is much heavier than the electron, so mu is almost equals to m, small m. However, this formula is only strictly correct in an inertial frame where the nucleus is considered fixed. Now, if we try to use the proton mass capital M in the formula, we run into a problem. This approach assumes the electron is fixed and proton moves. But that is a non-inertial frame. The law of physics, especially for energy calculations, only work correctly in inertial frames. So using capital M here is not valid. So let's start by looking at option A and why it is incorrect. We are focusing on the principal quantum number n, which appears in the denominator of the binding energy formula. So the principal quantum number n comes from the quantization of angular momentum and energy levels in the hydrogen atom. It's a whole number like 1, 2, 3 and so on. And it tells us which energy level the electron is in. No matter which frame of reference we choose, whether the electron is moving or the proton is moving, the value of n remains an integer. The quantum number doesn't depend on our choice of frame. So to sum up this part, n would still be an integer even if we switch frames. The way we describe the motion might change, but the allowed energy levels labeled by n do not become non-integer values. Let's focus on option B and why it's incorrect. The key idea here is the Bohr quantization rule doesn't just apply to the electron alone. Notice how Bohr quantization is about the whole system's angular momentum, not just the electrons. This means that if we apply quantization, we are considering the motion of both particles around their common center of mass, not just one moving around the another. This shows that the quantization conditions are based on the properties of hydrogen atom as a whole. It doesn't matter which particle we think of as moving. The rules apply to the system, so switching frames doesn't change the fundamental quantization. So to sum up this part, Bohr quantization is not limited to electron alone. It's a property of the entire atom, and that's why simply replacing the electron mass with the proton mass in the formula doesn't give the correct binding energy. Now let's focus on option D and why it's incorrect. The Bohr model uses the idea of circular orbits to simplify the motion of electron around the nucleus. Notice here that motion of the proton can also be considered approximately circular, just like the electron. The key point is that the physics of the orbit doesn't change just because we switch our frame of reference. The approximation is about the path, not about the particle is moving. To sum up, the main takeaway is that the circular orbit assumption in the Bohr model is valid regardless of which particle we consider as moving. The real issue with simply swapping the mass in the binding energy formula is not about the orbit shape, but about the correct use of reduced mass when both particles are moving. So let's examine next question about the Bohr model of the atom and why it doesn't work well for atoms with many electrons. Notice how the question asks you to think about what changes when you go from a simple hydrogen atom that has having one electron to more complex atoms with several electrons. This type of problem tests your understanding of atomic structure, especially the limitation of Bohr's model. 4 options are given and you have to choose the correct one. So the correct option is A, the electrons not being subject to the central force. So first let's recall with the what central force is. In the Bohr model, the electrons moves in a circle around the nucleus because the electrostatic force between the negatively charged electron and the positively charged nucleus pulls the electron directly towards the center. This force acts as the centripetal force, keeping the electron in its orbit, just like how gravity keeps the planets orbiting the sun. Now the Bohr model works well for hydrogen, which has only one electron. In this case, the electron feels a force only from the nucleus. So it's a simple central force situation. The model assumes that the electron's motion is determined only by this attraction to the nucleus, with no other complications. But things change in atoms with more than one electron. Here, each electron not only feels the pull from the nucleus, but also repulsion from all other electrons. These extra forces are not just directed towards the nucleus, so the total force on any electron is no longer purely central. This makes the situation much more complex than in hydrogen. So, because the net force on each electron isn't always pointing straight at the nucleus, the central force assumption of the Bohr model breaks down. This is why the Bohr model can't accurately predict the energy levels for atoms with more than one electron. The interactions between the electron make the forces non-central and much harder to calculate. First, let's focus on option B. We are going to see why this isn't the main reason for Bohr's model fails for multi-electron atoms. Electron colliding with each other is not the primary reason the Bohr model fails for multi-electron atoms. Let's dig a bit deeper. The real issue is that the Bohr model can't handle the complex interaction between electrons, especially the way they influence each other's energy through repulsion and screening. These effects change the forces acting on each electron, making the simple Bohr approach inaccurate. Now let's move to option C. We will see why this explanation, while closer, still isn't the full story. Screening effects happens when inner electrons partially block the attraction between the nucleus and outer electrons. While this is a big factor in multi-electron atoms, the Bohr model main flaw is that it assumes each electron feels a simple central force from the nucleus, which just isn't true when other electrons are present. So even though screening makes things more complicated, the real problem is that the Bohr model treats the atom as if only one electron is moving around a fixed nucleus. In reality, each electron feels a changing force because of all the other electrons. So the central force assumption breaks down. So other option D is incorrect because force between the nucleus and an electron is still given by Coulomb's law, but the presence of other electrons modifies the effective nuclear charge experienced by each electron. Bohr model failure is more about its inability to handle these modifications and the lack of a central force. Notice here that the presence of other electron changes the situation. Each electron doesn't just feel the pull from the nucleus, it also feels repulsion from other electrons. This means the effective nuclear charge, the net positive charge experienced by the electron, is reduced. So, whether Coulomb law still applies, the actual force is modified by these electron-electron interaction. Finally, the real issue with the Bohr model is that it can't handle these modifications or the lack of a single central force acting on each electron. The model breaks down because it assumes only one electron is orbiting the nucleus, which isn't true for larger atoms. Let's see next question. It's about the angular momentum of an electron in the hydrogen atom, specifically in the ground state according to the Bohr's model. Notice how the question highlights a key idea. In the Bohr model, angular momentum is treated as a vector which could point in any direction, suggesting infinitely many possible orbits. But in reality, this is not observed. The options test your understanding of why the Bohr model's prediction about the angular momentum directions doesn't match what we see in real atoms. This question checks your grasp of quantum mechanics concept, especially how angular momentum is actually quantized and restricted to certain orientations. Not all directions are allowed. 4 options are given and you have to choose the correct one. So correct option is A, because the Bohr model gives incorrect value of angular momentum. First, let's recall what the Bohr model says. In this model, the electron's angular momentum is said to be an integer multiple of h divided by 2 pi, which we call h bar, where h is Planck's constant. Now let's remember that angular momentum is a vector. That means it has both a size or magnitude and a direction in space. It's not just a number, it's an arrow pointing somewhere. If an electron were truly orbiting in a circular orbit or circular path, its angular momentum vector could point in any direction perpendicular to orbital plane. So if Bohr model were correct, there would be an infinite number of possible orientations for the electron's orbit, each with the same magnitude of angular momentum but a different direction. This would mean infinitely many possible orbits for the electron in the ground state, which doesn't match what we actually observe in quantum mechanics. In reality, electrons do not have an infinite number of possible electron momentum vectors. Quantum mechanics give us those restrictions. It tells us that angular momentum, just like energy, is quantized. That means it can only take on certain specific values, not any value at all. If there were infinite possible angular momentum vectors, it would simply imply infinite possible energy states, but in reality only one such state exists for the ground states. The Bohr model can't actually fix the direction of electron's angular momentum vector. Because of this, it gives us incorrect value of angular momentum. This is one of the reasons why Bohr model was replaced by quantum mechanics, which gives us more accurate predictions. Now let's focus on why option B is incorrect. The Bohr model doesn't actually account for the direction of angular momentum when it comes to quantizing the energy levels. Notice here that the Bohr model ignores the fact that in quantum mechanics the direction of angular momentum is also quantized. In the Bohr model, only the size of the angular momentum is fixed, not its direction. This means it can't explain why we don't see electrons orbiting in all possible directions. It's also important to remember that the lowest energy state or ground state is determined by the principal quantum number, which we called n. The direction of angular momentum doesn't affect the energy in the Bohr model. Now let's focus why option C is incorrect. We are going to break down the reasoning step by step. So first, notice that the direction of the electron's angular momentum is not always aligned with the electron spin. There are two separate properties. The orbital angular momentum comes from the electron moving around the nucleus, while spin is an intrinsic property of an electron itself, like a tiny bar magnet. To add to that, in quantum mechanics, the electron spin and its orbital angular momentum are independent quantum numbers. This means they can point in different directions and are not required to be aligned. Let's focus on why option D is incorrect. First, electrons do not move in strictly horizontal orbits. In the Bohr model, we might imagine flat circular paths, but in real atoms, the electron's position isn't fixed to a particular plane. Next, in Bohr model, the orbits are circular and can be oriented in any plane. That means if we stick to the Bohr picture of model, the electron's path could lie in any direction, not just horizontal. Finally, quantum mechanics replaces the idea of fixed orbits with probability distributions called orbitals. Instead of thinking about electron following set paths, we now describe where they are likely to be found. Let's solve this question about the oxygen molecule, O2 molecule, which is made of two oxygen atoms joined together. The question asks about the nuclear force between the nuclei of two atoms in an O2 molecule. Notice how the options focus on the importance and range of nuclear forces compared to electrostatic forces. This type of problem tests your understanding of atomic structure, especially the difference between the nuclear forces, which act inside the nucleus and very short ranged, and electrostatic forces, which act between charged particles and have a longer range. 4 options are given and you have to choose the correct one. Let's start our thinking process. Remember, nuclear force is the force that holds proton and neutrons together inside the nucleus. It's much stronger than other forces like the electric forces or gravity. Nuclear forces is indeed much stronger than the Coulomb's force, which is the force between electric charges, and also much stronger than the gravity, which acts between masses. Inside the nucleus, the nuclear binding force must overcome the repulsive Coulomb's force between the protons. This is why nuclei can exist at all. Without the nuclear force, the protons would fly apart due to their like charges. So the key point is that nuclear forces only dominate over the Coulomb's force within the nucleus itself, because the nuclear force is extremely short ranged. Once you move outside the nucleus, even by a tiny amount, the nuclear force drops to nearly zero, and only the Coulomb force remains significant between the atoms. So let's talk about the range of the nuclear force. Nuclear force is extremely strong, but it only acts over a very short distance, about a few femtometers, which is around 10 to the power minus 15 meters. That's much smaller than the size of an atom. So if two nucleons, meaning protons or neutrons, are farther apart than this, the nuclear force between them drops off very quickly and becomes almost zero. So let's compare this to the distance between the nuclei in an O2 molecule. The two oxygen nuclei are bonded together, but the distance between them is much larger than a few femtometers. In fact, it's on the order of 0.1 nanometers or 10 to the power minus 10 meters, which is about 1 lakh times bigger than the range of nuclear force. Because of this, the nuclear forces only act within each individual nucleus. They keep the protons and neutrons together inside one nucleus, but they don't have any effect on the other nucleus in the molecule. So in summary, the nuclear forces between the nuclei of two oxygen atoms is not important here, because nuclear forces are short ranged. Only forces that can act over larger distances like electromagnetic forces or electrostatic forces matter between the nuclei in a molecule. Now let's consider why option B is incorrect. First, notice that the nuclear force is not as important as electrostatic force when it comes to binding two atoms together. In molecules, the main force holding atoms together is the electrostatic attraction between the electrons and nuclei, not the nuclear force. Next, let's remember that nuclear forces act over extremely short distances, about a femtometer, which is 10 to the power minus 15 meters. This is much smaller than the distance between atomic nuclei in a molecule. The binding of atoms in a molecule like O2 is mainly due to electrostatic forces, specifically covalent bonding. Covalent bonds, atoms share electrons, and attraction between these shared electrons and the nuclei holds the atom together. Now let's move on to why option C is also incorrect. So nuclear force does not cancel out the repulsive electrostatic force between the nuclei of two atoms. The repulsion comes from the positive charge of the nuclei, and the nuclear force doesn't extend far enough to counteract this at the atomic scale. Remember, nuclear forces are very short ranged and only act within the nucleus itself. They are responsible for holding protons and neutrons together inside a single nucleus, not between different nuclei. So in contrast, the electrostatic force between the positively charged nuclei is a long-ranged and significant even at distances found in the molecules. The repulsive force is only overcome by the attraction between the electrons and nuclei in the covalent bonds, not by the nuclear forces. Now let's focus on option D and why it's incorrect. First, the fact that oxygen nuclei have equal number of neutrons and protons does not make nuclear forces important between the nuclei in a molecule. The balance of neutrons and protons affects the stability of each nucleus, but it doesn't change how nuclei interact with each other in a molecule. The forces that hold atoms together in a molecule are different from the forces inside the nucleus. Let's emphasize that nuclear force is extremely short ranged. It only acts over distances about the size of nucleus, which is roughly 10 to the power minus 15 meters. In a molecule, the nuclei are much farther apart. So nuclear forces doesn't play a role in holding the atoms together. Instead, chemical bonds like covalent bonds are responsible for the stability of molecule like O2. This is true no matter what the neutron to proton ratio is. Let's examine next question about what happens when two hydrogen atoms in their ground state collide inelastically. Notice how the question asks about the maximum reduction in their combined kinetic energy. This means we are looking at how much energy can be transferred from their motion to something else like exciting the atoms. This type of problem tests your understanding of atomic energy levels, specifically for hydrogen atoms, and how inelastic collisions can transfer kinetic energy into internal energy. 4 options are given and you have to choose the correct one. So first let's define the ground state. The ground state is the lowest energy level that an electron can occupy in an atom. For hydrogen, this means the electron is as close to the nucleus as possible and the atom is in its most stable form. Now let's talk about the energy of this ground state. In a hydrogen atom, the principal quantum number equals 1 for the ground state. Here we see the formula written out. E1 equal to minus 13.6 electron volt because En equal to minus 13.6 divided by n squared. This negative sign means the electron is bound to the nucleus. Energy must be supplied to move it to the higher level or to free it. If n increases, the energy becomes less negative, meaning the electron is less tightly bound. First, let's consider the total kinetic energy of two hydrogen atoms when both are in ground state. The ground state is the lowest energy level an atom can have. The initial kinetic energy is calculated as 2 times 13.6 electron volts, which equals 27.2 electron volts. Here 13.6 electron volts is the energy needed to remove an electron from the hydrogen atom in its ground state. So it's also the energy associated with that state. Now let's see what happens during the collision. The maximum reduction in kinetic energy occurs if one atom is excited from the ground state to the first excited state. Excitation means the atom absorbs energy and its electron moves to a higher energy level. The first excited state is the next available energy level above the ground state. It's technically possible for both atoms to be excited in a single collision, but usually only one atom absorbs enough energy to be excited while the other stays in the ground state. This is because energy transfer during collision often favors one atom making the jump rather than both at once. First, let's consider what happens after the collision. Suppose one hydrogen atom is excited from ground state to the first excited state, which is the n equal to 2 level. The total energy after the collision will be the sum of the energies of both atoms, one in the excited state and one still in the ground state. Now let's calculate the final kinetic energy. The energy of the hydrogen atom in the first excited state, n equal to 2, is minus 13.6 divided by 2 squared, which is minus 3.4 electron volts. The other atom remains in the ground state at minus 13.6 electron volts. Adding these together, next let's find the maximum loss in kinetic energy. This is simply the difference between the initial total kinetic energy and the final total energy after the collision. We will subtract the final energy from the initial energy to see how many kinetic energy was lost during the excitation. So the maximum kinetic energy loss is 27.2 minus 17, which equals 10.2 electron volts. This means that at most 10.2 electron volt of kinetic energy can be converted into an internal energy by exciting one hydrogen atom from the ground state to the first excited state during the collision. Okay, and this 17 electron volt final kinetic energy, this is the approximate value. It is 17 point something, but we have taken approximately 17 electron volt. So after subtracting it from 27.2 electron volt energy, it is coming 10.2, which matches our option. So this is all about NCERT exemplar of chapter atoms. I hope you enjoyed the session. Thank you for your attention.